going to wait for my sip of coffee. Ladies and gentlemen, there is one variable that plays a critical role in virtually anything we want to study, but it's often taken for granted. Does anybody know what that variable might be? Now it's my coffee sip.
Gravity.
Who said that? Kevin? Yes. Gravity. Gravity plays a critical role in virtually everything, and it's always taken for granted because, like, you're studying stuff in gravity, right? Well, let me give you two concrete examples, right? Even a germinating seed, this is like kind of mind-blowing. Even a germinating seed knows about gravity because when it germinates, the roots go down, the shoots go up. It's called geotropism. Your body knows about gravity in myriad ways because every time you take a step, your bones are compressed. And it sends a bioelectrical feedback back to your body saying, keep making those bones. Bones are really good. But if you go to the weightless environment of the International Space Station, there is no bone compression. The signal back to the body is, hey, you don't need the skeleton anymore. Go ahead and excrete it. And that's why astronauts have to work with pulleys and springs and mechanisms to compress the bones to minimize bone decalcification. Virtually everything is affected by gravity. So everybody see where we are with that, okay? So let's say that you have a flavor of essential question, which, by the way, is the flavor of question that drives all of microgravity experiment design, which is, I wonder what the role of gravity is in that, or this, or that thing over there. What is the role of gravity in something? That's a really powerful, important question. Well, if that's your essential question, your flavor of essential question, what needs to be the independent variable that you change?
Gravity.
You got to change gravity. If you want to understand the role of gravity in something, you got to change gravity and see what happens. But unlike changing the temperature or the humidity or the composition of the growth medium or atmosphere, you cannot change gravity. And the problem is this. Okay? So let me kind of provide some background in gravity so we can get to the next level. We don't know why, but any two masses in the universe attract each other with a force of gravity. Any two masses, like these two coffee cups. But you don't see these coffee cups flying towards each other because gravity is an incredibly weak force. For you to actually see gravity every day, to really notice that gravity is important and exists in your life, at least one of these masses has to be truly massive. So can anybody give me an example of two masses where one is massive and it leads to you seeing gravity every second of every day of your lives? In fact, you depend on it. Give me an example of two masses.
The Earth and the plate I dropped this morning.
The Earth and the what?
Plate I dropped this morning.
The plate?
Yeah, like a dish plate.
Who?
Like a cutlery plate hitting the ground when I drop it.
Okay, a plate. Well, I think the more yes, but I think the more personal thing would be this and you. The force of gravity exerted by Earth on you. And I'm not talking about just the mass under your feet, right? The force of gravity exerted by Earth, the Earth is 8,000 miles across, 12,000 kilometers across. It's a huge sphere of mass. And not just the stuff under your feet that you're sitting on is pulling down on you, but all of the continents, the mountain ranges, the oceans, the crust, the mantle, the outer core, the inner core, the entire mass of Earth is pulling down on you with a force of gravity, including the mass 8,000 miles below your feet. And so what do we call the force of gravity exerted by all of Earth on you?
Weight.
Your weight. Your weight. So when you step on a scale and you read 150 pounds in your bathroom, that's the force of gravity the entire planet Earth is mustering on you. which is kind of a statement about, yeah, this must be a weak force because it took the entire mass of Earth to pull down on you with 150 pounds of force. Okay, so now what do you intuitively think about the force of gravity between two masses when I move them farther away from each other?
Comes less.
It decreases, and that's intuitive because, like, the farther away they are from each other, the less they know of each other, the force of gravity is low. Okay, good. So a microgravity experiment is an experiment where you want to understand the role of gravity in something, which means you have to change the gravity variable and see what happens. Now that we've kind of talked a little bit about gravity, can you give me a possible experiment? This thing, I want to understand the role of gravity on this thing. So how do I do the experiment?
You do one version in a microgravity environment and then have a control in a gravity environment.
Okay, yes, though I haven't defined what microgravity is yet. So so all we know right now is that the force of gravity exerted by on anything we want to study is due to this. And we know that the force of gravity exerted between two masses decreases with distance. So just based on those two pieces of information, Shannon, how would you recraft your experiment?
I would do one very far away from Earth,
Right?
and then the control would be on Earth.
So what Shannon is saying, which is like really great, is that if you take the experiment far from the Earth where gravity is less, and then you do the same experiment in Earth gravity, when you bring the experiment back from deep space and you put them side by side, this one operated in lower gravity, this one operated in Earth gravity, which means that you've changed gravity and you can see if there are behavioral differences in what you're studying to understand the role of gravity in that. Does everybody understand that concept? Does that all make sense? Okay, now let's see if we can do what Shannon just said, all right? So what's the tallest mountain on Earth?
Everest.
Everest. Well, actually, I said that badly because the tallest mountain on Earth is actually Mauna Kea. But the tallest mountain on Earth above sea level, as Kevin said, is Mount Everest. It's not tall enough. I need to find me a mountain 47 times higher than Mount Everest. 47 times higher than Mount Everest. And what's cool about that mountain is if I go to the top, I'm 250 miles above the Earth. Does anybody want to tell me what they think I might find 250 miles above the surface of the Earth?
The International Space Station.
The International Space Station. So when I'm standing on top of Jeff's mountain, I can wait, and then the International Space Station flies right by my face, and I look through the big window, and I look inside at the astronauts. Now, have you seen videos of astronauts in space? Can you characterize what you saw?
They float.
They're floating around as if what is missing?
Gravity.
There's like no gravity. They're floating around. There's no up or down. Those astronauts have no gravity, not some gravity, no gravity. Okay, that's what we call a weightless environment. Why is it called weightless? Because the force of gravity exerted on you is your weight. They don't seem to have any weight, so it's a weightless environment. A microgravity experiment, that really technical term, really means an experiment in a weightless environment. That's what microgravity means. So designing a microgravity experiment is designing an experiment to be done in a weightless environment. Now, here's the problem. I go to the top of my mountain. I have to admit that I have this problem. I'm working on it. I promise I'm working on it, but I seem to have to take my bathroom scale everywhere I go. So I'm on the top of my mountain at 250 miles above the surface of the Earth. The International Space Station flies right by my face. I look through the big window and I see the astronauts floating around. They say, "Hey, Jeff, look, there's no gravity here." And now I'd like you to all answer as your students, okay? I now stand on my bathroom scale, and what do I weigh? Whatever you, no wrong answer. Go ahead, just shoot out an answer.
My students would say 0.
0. So what Krista's saying is a logical answer is, well, if you're at the same distance above the Earth as the astronauts and there's no gravity for them, there's no gravity for me. I can't even stand on my scale. I weigh nothing. Anybody else have another possibility?
I would assume that you would weigh less. Right?
He's thinking. Look at him think. That is so cool. We see, that's what it's all about.
I would assume somewhat less because you'd have the field of gravity would be weaker further from the center, therefore less of it would be acting on you, but there would still be weight nonetheless.
Very good. So it turns out that when I stand on my scale, I weigh 90% of what I weigh on the surface of the Earth. Almost the same as what I weigh in my bathroom at home. Now we got to understand this, okay? The force of gravity exerted by the Earth is where this is all coming from. What's the diameter of planet Earth?
25,000 miles.
Actually, that's the circumference
Oh,
of divided by
sorry. Yes.
3.14.
Yes.
So it's
8,000.
8,000 miles across. Now, you know, I'm a firm believer in the MKS system,
Mhm.
but I'm also a firm believer in building bridges to the familiar. And education ought to be about a emotional, guttural response when that light bulb goes off over your head. If you're simply asking students to memorize stuff, that's not learning. But if you build a bridge to the familiar so that they emotionally deeply understand what you just said, that's when learning takes place. So I could do this in kilometers, I could do it in meters. I'm going to use units that we all know because we're familiar with miles. So it's 8,000 miles across. How high is the mountain that I'm standing on above the surface of the Earth?
29,000.
How much?
29,000.
Oh, that's in feet.
Oh, yes, feet.
Right. So in miles, how high is, where's the International Space Station, which by the definition is the same height I am above the surface of the Earth? How high above the surface of the Earth is it?
Really close to the surface.
Okay, that was a good way out of the answer. Very good. Okay, I said it before,
150.
250 miles above the surface of the Earth, right? 250 miles above the surface of it. 8,000 miles across, 250 miles above the surface of the Earth. Is the top of my mountain, hence the International Space Station, out here? Tell me when to stop.
Keep going.
Mm-hmm.
Keep going. Okay.
Like right here. The International Space Station is skimming the surface of the Earth just above the atmosphere. You want something for climate change, and oh wow, for climate change, to put this in perspective, the atmosphere compared to the Earth is thinner than the skin of an apple compared to an apple. Okay, do you feel that? Did you feel what I just said?
Mm-hmm.
That's building the bridges to the familiar. Okay, so the International Space Station is just skimming above the surface of the Earth. Has it gone very far from the Earth, Ishaya?
No.
No. So what can you say about the force of gravity exerted by Earth on me on top of my mountain?
The force has barely changed.
Has barely changed. It's still 90% of what I weigh on the surface of the Earth. That's why I haven't gone far from the Earth. What's the problem?
There's still going to be a strong influence of gravity in the experiment. We're only, as you said earlier, experiencing about a 10% shift in the strength of gravity.
Yes, exactly. Except the problem is due to those videos you were watching.
Me?
The astronauts are at the same distance from the Earth as I am on top of my mountain, which means the force of gravity exerted by Earth on them, their weight is 90% of what they weigh on the surface of the Earth. The astronauts cannot be weightless. They
Well,
are weighted. The force of gravity exerted by Earth on them, their weight is almost identical to what they weigh on the surface of the Earth. So now, what's the problem?
their relative, the velocity that they have is
Well, you're
preventing
giving
gravity
me
from
the
acting on them.
you're giving me the explanation. What's the problem?
That is an interesting question.
Anybody?
Have to do,
I will tell you the answer. Say, go ahead, Kevin.
does it have to do with the rate of travel?
Okay, you're trying to come up with an explanation. Let me give you. The problem is that I'm asking a vague question. Let me just define the problem. The problem is that if the astronauts weigh almost the same as what they weigh on the surface of the Earth, why the heck are they floating as if there's no gravity whatsoever? That's the problem, right? That's the problem. I have no idea what's going on there. So I'm going to walk you. Let's see. We started at 11:30. Okay, good. So let me walk you through this, and we're going to have to go through this quickly. All right. I'm a New Yorker. I'm so sorry. Apologies. I'm a New Yorker. My favorite building is the Empire State Building. I love the Empire State Building. And what's cool is you can take an elevator from the ground floor up to the 104th observation deck. One elevator all the way to the top. Now, is the Empire State Building a big structure on the surface of the Earth?
Relatively no.
Relatively no. How does it compare to Mount Everest?
Tiny.
How does it compare to a mountain 47 times higher than Mount Everest? Like
Negligible.
insignificant. So if I go to the 104th floor of the Empire State Building and I told you, I bring my bathroom scale wherever I go. What will my weight be on the 104th floor?
Effectively the same as it is on my ground level.
Yeah, the same as on ground level. My bathroom scale is not going to see a difference in 104th floor. I'm going to need a really, really sophisticated piece of equipment to see something like that. Okay, so now I take the elevator to the 104th floor, and here is something that's really important. There are no windows in the elevator. Okay, so I take the elevator to the 104th floor. I bring my trusty bathroom scale with me. And you know what else I did, which is I took a chair from a local kindergarten before I went to New York. And that
Evil.
chair is kind of cool. It's a real sturdy chair. But if I stand on it, I'm only a foot above the floor. It's a tiny, sturdy chair. So now I go to the 104th floor in my elevator, and the doors open up. And I see people walking around on the 104th floor. It's like the elevator's part of the 104th floor. And I do my experiment. I get up on my kid's chair. I'm a foot above the floor of the elevator. The bathroom scale is beneath me. And I step down on the bathroom scale. And what do I weigh? I'm in the elevator, 104th floor. The doors are open. The elevator is like part of the 104th floor. I get up on my 1 foot high chair and I step down onto the floor, the bathroom scale in the elevator. What do I weigh?
Are you giving it time to rest or at the instant of impact? What do you weigh?
I give it time to rest like I do in my bathroom at home.
And the elevator's not moving?
And the elevator's not moving.
You weigh the same amount.
Yeah, no, it was not a trick question. Okay. I weigh exactly what I weigh on the surface of the Earth in my bathroom. I can't tell the difference. Now, I don't know if you all know this. Most of you know this. Science is about reproducibility. So I'm going to do my experiment over again because that's what scientists do. We love doing that. So now I get back on my chair and the door is behind my back. I can't see the door. And the door very quietly closes behind me. And the moment I'm walking off my chair, somebody does something really bad. They cut the cable holding the elevator. What happens to the elevator, me, the bathroom scale, and the chair?
It free falls down the shaft.
Okay, so let's kind of unpack that. We fall. What is happening to the speed as time ticks away? What's happening to the speed?
It's increasing at 9.81 meters a second up to terminal velocity.
Okay, so it's increasing. So we call that an
Acceleration,
Acceleration. And what's causing the acceleration?
gravity.
Gravity. And what do we call the force of gravity exerted by Earth on the elevator?
Wait.
The elevator's weight. So the elevator is falling under its own weight. Oh, that's where that expression comes from. Okay, now, will it keep accelerating?
Yes.
Up to a point.
Up to a point. Okay, what? Okay, so first of all, let's not think about the splat on the bottom. Okay, that's not part of the thought experiment. But you said it will accelerate up to a point. What does that mean?
There will be a point at which, from my understanding, it cannot accelerate, or the air it's interacting with is preventing it from accelerating further past a point because it cannot move out of the way fast enough.
So what Ashay is saying here is that there's air in the elevator shaft, and it causes a drag force on the elevator car. Well, if I jump out of an airplane, right, for the first few seconds, I'm accelerating under the action of gravity, but the air that's pushing on me, its resistance depends on how fast I'm moving. The faster I move, the more air resistance there is until finally I can't go any faster. What is that called?
Terminal.
Terminal velocity. And for a human being, it's about 100 miles an hour. I can't go any faster, but I can't survive landing at 100 miles an hour. So I better deploy a parachute, which will increase the drag dramatically to slow me down to a point where I can parachute another day. Okay, so here's the deal. I suck all the air out of the elevator shaft, and I make sure that the car of the elevator, as it's going down, is not rubbing up against the sidewall, so there's no friction. So once the cable is cut, what is the only force acting on the elevator?
Gravity.
Gravity. And what do we call falling when the only force acting on an object is gravity? What do we call the kind of falling when the only force acting on an object is gravity?
Free fall.
Free fall. It's free of any other forces. Now, will it keep accelerating?
Yes.
Yes, it'll keep accelerating up until splat. Okay? It'll keep accelerating. And now, Ashaya, you told me what the acceleration due to gravity is.
9.81 meters. That's round technically.
9.81. What are the units?
Meters per second squared.
What does that mean?
Every second over the last second, the speed of the object will increase by 9.81 meters per second. But it's
Yes. So what he's saying is that 9.8 meters per second squared means that every second the speed increases by 9.81 meters per second. I have no idea what that means. I don't think in those units. So I'll give you a bridge to the familiar. The acceleration due to gravity is such that every second your speed increases 20 miles an hour. So after 1 second, how fast are you moving?
20 miles an hour.
I'm sorry?
After 1 second, starting from zero, you'd be at 20 miles an hour.
20 miles an hour after 10 seconds.
200 in free fall.
200 miles an hour. After 100 seconds, if you take out the splat, after 100 seconds, how fast are you moving?
2,000.
2,000 miles an hour. The acceleration due to gravity is huge. Okay, so here's the deal. I step off the bathroom, I step off the chair, and at that moment I'm stepping off the chair, somebody cut the cable holding the elevator, and all of a sudden the elevator starts to accelerate down, as do I, the bathroom scale, and the chair. Are we all accelerating down at the same acceleration? We're accelerating down together. Anybody? Okay, Krista says, I don't think so. Okay.
There's slight differences.
Slight differences. Okay, so let's do this following thought experiment. I've been working out in advance of this Zoom video conference. To prepare. I'm a big guy. I'm nice and strong. In one hand, I hold a Toyota Camry. I told you, big guy. I'm holding a Toyota Camry in one hand and a bowling ball in the other hand. If there's no air in this room, when I drop them, they're both going to be in free fall. If I drop the Toyota Camry and the bowling ball from the same height at the same time, will they hit the ground at the same time?
Yes, because there's
Okay,
no.
Krista says yes, but she said no before.
I was thinking elevator on Earth, so I was thinking
Okay,
air
well,
resistance.
let me just keep going with this
Yep.
with this explanation.
Yep.
The Toyota Camry has a certain amount of mass. Is it possible I can think of the Toyota Camry in bowling ball masses? In other words, the Toyota Camry is the equivalent of 462 bowling balls, if I don't include the options package. Okay, so this Toyota Camry is the equivalent of 462 bowling ball masses. So instead of dropping the Toyota Camry, let's drop 462 bowling balls here and my other bowling ball here. So now I'm dropping 463 identical bowling balls from the same height at the same time. Will they hit the ground at the same time? Sure, they're all the same. So the acceleration due to gravity has nothing to do with the mass that you're dropping, which is why when I asked Ashaya, what is the acceleration due to gravity? He said 9.81 meters per second squared, and there was no mass multiplying that. Okay? And if you look up a YouTube video of an astronaut on the moon with a feather, so astronaut moon feather, you will see an astronaut that drops a feather and a hammer from the same height at the same time. And because they are in free fall, there's no air, the feather and the hammer hit the ground at the same time. So does that mean that me, the bathroom scale, the chair, and the elevator car are all accelerating down together? Yes? Okay, so here's the deal. If Jeff goes down 100 feet in a certain period of time, let's say 10 seconds, if Jeff goes down 100 feet in 10 seconds, will the elevator floor also go down 100 feet in 10 seconds?
In vacuum free fall?
Yes, in free fall.
Then yes.
If we're all going down this together, if I move down 100 feet in 10 seconds, the elevator floor moves down 100 feet in 10 seconds. Can I catch the floor?
No, you're going to be locked in position unless some sort of force acts on you.
So what you're saying is I cannot catch the floor. So I did the experiment over again exactly the way I did it before. I'm on the edge of the chair, a foot above the floor. Somebody cuts the cable. I didn't know that, right? And the moment I'm walking off the chair, that's when the cable is cut. And now everything starts accelerating down. What do I see in my elevator?
Do you have momentum moving down prior to free fall beginning?
No.
Then you just kind of get frozen in place as everything falls.
So
But your
floating.
change, you would not perceive a change in your position or the elevator's position.
So what you're saying is I'm floating a foot above the floor. Because every time I head towards the floor a certain distance, the floor moves away from me at the same distance. I can't get to the floor. I did the experiment over again, and now, for some crazy reason, I'm floating in the middle of the elevator as if somebody turned off the gravity switch. There is no gravity perceived in my elevator. Now, do I see the floors of the Empire State Building flying by me at an ever-increasing speed?
Yes, but no, you said there's no windows.
There's no windows. There's no windows. I still hear Barry Manilow playing on the sound system. It must be Bluetoothed in. So here's the deal, okay? It is the force of gravity exerted by Earth on the elevator, the bathroom scale, the chair, and me that are causing us to accelerate at a fantastic acceleration. But inside a freely falling laboratory, everything will behave as if gravity is turned completely off. Does everybody understand what we just came up with? I mean, that's like a way cool concept. You may feel like that can't be the way the world works. Yes, it is. And so here, I don't know if you knew this, but I'm an alien from another planet because I've been talking to you right now with no air in this room. And so I'm actually just sending my thoughts to you and you're picking them up, but you think I'm talking, okay? There's no air in this room. If I drop this ping pong ball, is it in free fall?
With no air in the room, yes.
Yeah, it's in, whoops. Come back. Come back here. All right. If I drop this ping pong ball and there's no air in the room, it's in free fall. Good. What happens if I throw this ball with a little speed? What's the trajectory? What's the path?
It'll stay horizontal.
It'll go horizontal, but then what will happen?
It'll curve off.
It'll
and
curve
fall
and
to
it'll hit the ground. What happens if I throw it a little faster?
The rate of there'll be a lesser rate of change as it falls. It'll take longer to hit the ground.
So it'll go farther and then hit the ground. Okay. Now, a force is a push or a pull. I'm pushing it, right? I'm pushing it. It's starting from rest. And that force I'm applying is having it come off at a certain speed, right? But once it leaves my fingers, I'm not pushing it anymore. Once it leaves my fingers, is it in free fall? Once it leaves my fingers, what's the only force acting on the ball?
Nothing.
Gravity.
Gravity.
Oh, gravity. Yeah.
The only force acting on the ball is gravity. So if there's no air in this room and I throw the ball, that was free fall. And if I keep throwing it faster, it'll go farther away before it hits the earth. And if I keep throwing it faster and faster and faster and faster, it will move so far that as it arches, it will swallow the entire planet Earth. And I can catch it in my hand on the other side in 90 minutes if there's no atmosphere on Earth. So this is the elevator. This is the International Space Station. The International Space Station is the elevator. The astronauts are in free fall. And anything that you place in a freely falling laboratory will behave as if gravity is turned completely off, even though they are skimming the upper atmosphere. They're above the atmosphere. And so, does everybody understand this story? Okay, now let's go back to a microgravity experiment. And Shannon, now you can frame the experiment the way it should be framed. If I want to understand the role of gravity in something, how do I do the experiment?
You do one version in your microgravity environment and the control in your gravity environment. So Earth versus ISS.
So microgravity, again, is weightlessness, which means that if you do your experiment in a weightless environment on the International Space Station and you do the control on the Earth and you bring the flight experiment down, you put them side by side, you're looking for behavioral differences in what you're studying. That's all a microgravity experiment is, right? Well, we can't change the force of gravity. We can't get far enough away from the Earth to make a big enough difference in gravity. So we trick the experiment. We drop it. We put it in a continuously freely falling laboratory, and the force of gravity exerted by Earth on the International Space Station and the astronauts are what's causing it to go around the Earth. It's falling around the Earth as opposed to flying off into deep space. Does everybody understand what I just walked through? Now, here's a shortcut. Here's an important shortcut. Once you understand classic experiment design, and then you say microgravity experiment design is an experiment in a weightless environment, you understand right away that the way to do this experiment is to do, as Shannon said, do the experiment in a weightless environment on ISS and do the experiment on the ground. And that's all you need to know. What it doesn't tell you is why it's a weightless environment on the International Space Station. If you want to not go into that storyline, you don't have to, but I can tell you that most students think the reason the astronauts are weightless is because there's no gravity in space. And that can't be a worse misconception to an astrophysicist. So does everybody understand how simple a microgravity experiment is?